Hello. Well, I love a productive all-nighter, and I refuse to have a second one. So, follow-up video. I made this very primitive. This thing is a H bridge, not appeared on camera before. I had to go and replace a few resistors and so forth to change some of the values. This here is one of my H bridge drivers. It's just using 5x5 timers and so forth. But essentially what I'm now doing is I'm putting square waves into this ferrite transformer with a simple half ohm ballasting resistor, and it's working. Square waves are working. It was absolutely no problem at all. I didn't need a correction resistor, a correction capacitor, or an inductor to get it resonating. It's got a very natural resonant action to it. So yeah, 18 volts going in. That's currently across the coils, or more specifically across, good question actually, what is it across? Yeah, it is, it's straight across the coils. I've got yeah, the coil is coming out, not running through that resistor, and just yep, through this piece of gratuitous extension cord, and back out here, no mains connections. So what we can do, the current flow 20 milliamps, so naturally we have no light, but what I'm going to do is just tune it a bit. I'll make sure we got a bit more duty cycle. It's a bit of a manual tuning process. Basically, the frequency and the duty cycle are not locked. So if I've got a 20% duty cycle at 1 kilohertz, and then I turn the frequency up to 2 kilohertz, then I've got a 40% duty cycle. So they, oh, I mean, sorry, they are locked. They are locked together. So it's a bit awkward to tune. And it's quite dangerous too, because obviously if you get beyond 100% duty cycle, then you're shorting your H bridge. But that's okay. It's quite easy with these globes. You tune it for maximum light, and then the fine tune knob, fine tuning to about there. And quite low on the duty cycle, as I found something that's best. And yeah, anyway, so there's 18 volts going in. That was a pretty quick tune job. I had it looking a bit better before, but that's 140 milliamps, and the signal on the scope, if I give the frequency a bit more of a fine tune, it'll bring the duty cycle down because of that locking issue. Oh, gone a bit too far. But yeah, very much looking like this sawtooth wave sign. Yep, pretty clear cut. Nice little demonstration of the Mr. Previous circuit, and more importantly, some of the circuitry I put together when I was drunk a couple of weeks ago, and obviously it works very well. So I've got it a bit overdriven now. The current's such a fine line. If I overdrive it ever so slightly, it makes almost no difference to the globe, but the current shoots up. So yeah, 100 milliamps and 18 volts. But yeah, with a bit of fine tuning, that'll come up really well. And yeah, so the next coils and the next part of the experiment. So stay tuned. It's all coming together. This here, my dear friends, is a cup of coffee. This is the Mr. Prever experiment. We have a large number of coils and cores to go through. But look at this. This is a sweeping signal generator. It runs sweeps. You have the audio transformer back from a last video. These 3 light globes back from a last video. And the sine wave input. The audio transformer is going into this globe, which is then branching out into 2 globes parallel through the core and back out again. So this is in series. So this should always be the brightest globe, but it is not. It is not. We have an oscillating function, this tank circuit, and that is going to yield some results today because we have a lot more cores to test. And I suspect we're going to see some more magic. 9 o'clock in the morning. This is the most civilized time to be making a video. I neglect to mention, of course, that I haven't slept yet. My new sweeping signal generator has arrived, and I ask you, when you have 2 light globes that are parallel, and that's in a series circuit with a transformer on one end and a globe on another, on either side should be having the most power throughput, yet we don't. This tank circuit has the most power here, which is odd because this represents how much power we're putting into the system. And these are low frequency sine waves, about 1 kilohertz. Nothing fancy, just magic. So we've got a pile more stuff to test, and I want to improve on this today. I want more magic. More magic! Thank you. Observation number 1. This quote-unquote tank circuit, otherwise known as bucking coils or partnered output coils, as Tesla and so forth put it, the effect that we're looking for, the effect that I have here, we are now doing a frequency sweep from 1 kilocycle to about 4 kilocycles, or starting off a bit lower. Every 5 or 6 seconds it's running a frequency sweep. It's actually starting at about 500 Hertz. Now this effect completely goes away, vanishes. The effect that we're looking for is absolutely non-existent if we switch one of these coils back to front. They have to be wired back to back. Okay. Okay, second observation. It behaves more conventionally in every way. Okay, let's see what else we can learn. Well, I looked up at my scope and I have learned something else. Two traces, both set to the same voltage reading, are completely 180 degrees out of phase. That will be these 2 globes here, 180 degrees out of phase. And there's a lot of current going through the circuit, which we are paying for. So if we clamp the core back together, there's greater impedance, so we're paying for less energy, yet we're still able to utilize some that we're not paying for via the resonance in the core. And what changes then is the phase shift on the oscilloscope. I will demonstrate that. Only very slightly out of phase. Enough to give us an effect that we're looking for, but not enough to give us everything that we're looking for. We want more, shouts Gandalf across the plains. We want more. By the way, these two coils that we've been using thus far, one of them is 1 ohm and the other is 0.6 of an ohm. Interesting. Well, so are these. Let's see what happens. Thinking. Well, these coils are modelled on some friends of mine who are using a 500 ohm coil and a 1500 ohm coil. So I've found 3:1 ratio works best as well, but I've done 120 ohms and 360 ohms. So yeah, still really high ohmage. But I found that at Resonant, there was no throughput at all. None at all. Obviously, out of resonance, the globes are not going to light because the globes are perhaps 3 ohms, and being, you know, a couple hundred ohms, only a few % of the power is going to the globes, so the globes aren't going to light under resistive conditions. But under resonant or inductive conditions, in resonance, the internal resistance of coils in resonance drops to almost 0. Resonating coils become almost superconductors. I might have to check that, but I'm pretty sure that's the case. So yeah, even at resonance, I was not able to get any throughput. However, these are E-cores, ferrites, taken from a ATX power supply. They are very cheap. They are working, but not at those frequencies. At those frequencies, at those resistances, I'm going to require something really special. And he's spent $800 on some cores. I haven't done that, but more tests are going to proceed because I'm not satisfied with just getting stupendously good results from spending money. I think I would quite like to use my skills in power electronics, and by raising the voltage really high, I think I can get these cores to play ball. So there's a few future experiments to come, and one of them is a Chinese replica of those $800 cores, which I only paid $30 for. So that's another experiment that's coming up shortly. So yeah, we're going to crack this thing. Thank you. Well, this is the core I was just testing. I've run a sweep on every single one of those coils, and they tell a bit of a story. The main observation I've gleaned from this is that the lower the resistance on the coils, the better they seem to work. And as promised, another factor I told and have proven out is that a 3:1 ratio works best. The coils have to be wound back to back. You want a 3:1 ratio and keep the resistances low. So I've proven that basically on all the cores I've tested. So what I could do is go on testing cores. There's quite a large variety. Quite a few different compositions, quite a few different styles. Most of these are salvaged from one place or another. Some of them are purchased. But what I want to do instead is some practicality testing, because at the moment we're running a sine wave from a signal generator, and there's a few problems with that. In the future we're going to need higher frequencies for the better cores, and unfortunately it's very difficult to get a high power sine wave generator. It's that's just not happening. So we've got to abandon this notion of using audio amplifiers as a kind of a shortcut to getting some success. It's great for testing, but it's not a practical proposition in the long term. So what needs to occur is that I need to solve that problem. I either need to get a high-powered, high-frequency audio amplifier, and I'm not sure they exist for any reasonable price. It's not a good way to base experiments on. So what I'm going to have to do, scratch his chin, is the next experiments I'm going to make are in two things: raising the voltage to make these ferrite cores, these common ferrites, and even iron cores more accessible to the mortal man. So, and running square waves. I'll just slide that one in at the end. That one might be a little difficult because I've noticed previously on a frequency with this particular core that it works with a sine wave generator. It just completely refuses to work with square waves. Absolutely no action whatsoever. However, there are certain things you can do with square waves to turn them into something like a sine wave. Well, capacitors for one. You can have a parallel capacitor with the core, or you can have a series inductor, and both of those will kind of trim a square wave into a sine wave to some degree, and that has been done with the system I'm trying to copy, these bucking coils. It has been successfully demonstrated, but I can't say to what degree. I can't say how successful it was. These globes here are producing a little more light than they should be for the input power. It might be 120% efficient. By attempting what I'm going to do, trying to have my butchered sine waves from square waves, I might lose that extra efficiency, but I might also be able to raise the voltage and gain 10 times that back. Really can't tell. So that's where we're going to take it from here. So the next video might not come today, it might not come tomorrow, but hopefully it does, because this does sound very challenging, but also it's somewhat of a tipping point, I think. So if I can succeed at this, then the project will succeed. So there's only one way forward, and it's to raise the voltage and pull out the square waves. This is going to be a challenge, a real one. This is not testing, this is not playing around, this is not experimenting. This is hard engineering that lives do depend on. So, come back and watch the drama. Thank you. Now, before I do go on with those other square wave experiments and so forth, I did want to try one more thing. 3.6 kilohertz was the peak for the core I was using, and before I went on, I wanted to try with just 18 turns of wire and 6 turns of wire and see what occurs. and basically the effect is here, but it was extremely difficult to find and almost completely worthless. The parallel globes do have more light than the series globes, but I didn't find it at 3.6K, which is where I found all the others. With just a few turns of wire, this came in at 42K. The frequency is so high that I just can't push any power through it. So yeah, anomaly. I don't understand this. Everything else makes sense, but this I do not understand. So we'll definitely come back to this later. Well, I decided to quickly wind one more, just because I can. So I went for 9 ohms and 4 ohms. And I'm glad I did, because this one is quite remarkable. It is better than all the rest by a large margin. The range in which the secondary globes are brighter is throughout the range. Instead of 3.6K for one, 3.6 for another, 750 Hertz for one, and 1.3K was the absolute peak on this one. However, this one spread from perhaps 500 Hertz all the way up to, when the audio frequency cut out, about 38 kilohertz. So the effect was there right throughout the range. So yeah, an incredible difference just by changing the resistance values. So we might be in for a lot of tedious winding in future, but for the time being I've got quite a few to test with, so let the party proceed. Let's find other ways to improve it.